All right, this video is going to cover Chapter 5, Sections 1, 2, and 3, the beginning of which is the angles in a triangle. Hopefully a lot of that stuff is review. We start by defining a triangle, and a triangle is a figure formed by three segments joining three non-collinear points. So segments meaning they have to be straight sides. Three non-collinear points mean two of them can lie in the same line. Well, they all have to in pairs, but that third would be non-collinear. A point where the segments meet is called the vertex. So each of these points would be referred to as individually a vertex, plural, vertices. The sides are all segments, which would be AC, CB, and AB. We can name it saying the word triangle ABC, or you can also use the symbol of the triangle followed by the three letters. Vertices you list as those points, sides as those segments, and then angles A, B, and C. We're going to classify it first by their sides, the type of sides. If no sides are the same or no two sides are the same, then it is a scalene triangle, so three different length sides. If at least two sides are the same, it's isosceles. And notice the word at least, because equilateral is all three sides. But because this says at least, it means an isosceles, or an equilateral, is also isosceles. If you do see three sides that are the same, though, and it says what's the best way to describe this figure, it would always be equilateral over isosceles. Now we're going to classify by the angles. So if all of the angles are less than 90 degrees, it's an acute triangle. If one angle is greater than 90 degrees, it's obtuse. If one angle equals 90 degrees, it's right. And if all of the angles are equal, it's equiangular. So just some pictures of examples underneath. Acute, right, obtuse, and equiangular. The triangle sum theorem says that the sum of the measure of the interior angles is 180 degrees. So all the angles in any triangle add up to 180 degrees. The exterior angle theorem says the measure of the exterior angle of a triangle equals the sum of the measures of the two remote or non-adjacent interior angles. And what this means is if you have an exterior angle, so for example, this angle that's out here, it's equal to the sum of the two angles that are not next to it. So next to it would be this interior angle, not that one, but the sum of the other two. So angle 1 in this case is equal to the sum of angle A and angle B. You could get there the long way by adding the three angles inside the triangle, subtracting them from, or adding the two angles, inside the triangle and subtracting it from 180, and then using the linear pair. But this is a shorter method. Just add up the two angles inside the triangle, but not next to the angle you're looking for. Okay, a corollary, so this is a new term. A corollary to a theorem is defined as a statement that can be easily proven by a theorem. So basically this just says if someone has made the discovery of the theorem, a corollary is something that kind of piggybacks off of it. That would be easy to figure out based on that. So the corollary to the triangle sum theorem says that the acute angles of a right triangle are complementary. And this should make sense common sense wise. If the three angles inside the triangle have to add up to 180 and one of them is 90, if I take away that 90, the other two have to add up to 90 degrees, which is all this is saying. So acute angles of a right triangle are complementary. All right, example 1. State whether the triangle with the two angles having the given measure is acute, right, or obtuse. So the first thing we have to do, because they are giving you only two of the angles, is find out what the third one is and then classify it. So if I add up the 55 and the 43, I get 98 degrees, and 180 minus 98 degrees is 82 degrees. So an angle or a triangle with the measurements of 55, 43, and 82 are all acute. Go to the next one. 47 plus 43 is 90 degrees. which means that missing angle is 90 degrees, which makes this triangle a right triangle. Go to the next one. 80 plus 75 is 155. So 180 minus 155 is 25. And all of those angles are acute, which means my triangle is also acute. Going to the next one, 33 plus 33 is 66. 180 minus 66 is 114. And that tells you that that last angle is obtuse, which classifies this triangle as obtuse. And 24 plus 66 is 90. That last angle is 90, and this triangle is right. All right, example 2 says find the measure of angle A. So here we're going to put together some prior knowledge. For example, in A, we've got vertical angles. So we don't know all 3 angles in the triangle on the left, but we can find it. If I do 80 plus 50, I get 130. 180 minus 130 is 50. So this third angle here is 50. Its vertical angle would also be 50. And then 50 plus 50 is 100. Subtract 100 from 180. And I get angle A is 80 degrees. If you're looking at B, you've got these 2 congruent angles. So in my bottom triangle, I've got 60 and 40. Add that together, that's 100. Take it away from the 180. And I got the congruent angle to be 80, which means this is also 80. And this means this is also 60. So angle A is 60 here. And lastly, in C, you've got 30 and 110, which is 140. Subtract that from 180. I get 40 degrees. This would also be 40 degrees. Together, this is 70 degrees, which means that remaining angle is 110 degrees. All right, example 2, continued. Find the measure of angle A. In D, you're looking at an exterior angle here. And remember, the exterior angle is equal to the sum of the remote interiors. So 120 equals 80 plus angle A, which means if I subtract that 80, angle A is equal to 40 degrees. And in E, it says in triangle EFG, angle G is 100. The measure of angle FEH, which is this out here, is 3 times the measure of angle F. Find F. So if F is our X, then this is 3X out here. And 3X equals the sum of the remote interior, which is X plus 100. Solve by subtracting X from both sides. 2X equals 100. And X equals 50. All right, 5.2 is called congruent polygons. So we get to branch out beyond triangles here. Congruent figures are 2 figures that have the same size and shape. So they have to both be triangles, or both be quadrilaterals, or both be hexagons, or pentagons. Whatever that shape is of the first one, it has to have the same shape in the second one. And they have to have the same size. All the corresponding parts of one figure are congruent to the corresponding parts of the other. So all the sides have to have a pair. In this diagram, AB matches EF. AC matches FD, and BC matches ED. And for angles, A matches F, B matches E, and C matches D. So the order of the letters of how we name it is also important. If you go the single arc, which is angle A, then the double, which is B, then the one with 3 arcs, which is C, and you say it's congruent, you'll see that same congruent symbol. You have to go in the same order the second time. F was the single arc, E had 2 arcs, and D had 3 arcs. So the order of the letters is important here. All right, third angles theorem gets added to our theorem list. And it says if 2 angles of one triangle are congruent to 2 angles of another triangle, then the third angles are also congruent. So if you have 2 pairs marked as congruent, like B matches E and A matches D, then you can gather or decide that the last 2 angles, which are the last pair of angles, are also congruent. And that's called third angles theorem because it's the third angle in each triangle. All right, so property of congruent triangles. Just like before when we did property of angles and segments, we can do properties of triangles. The reflexive property says any triangle is equal to itself or congruent to itself. The symmetric property says that I can switch the order of the names around, so not the letters themselves, but the actual names. If ABC is congruent, triangle ABC is congruent to DEF, then DEF is congruent to ABC. And the transitive property is the if and then statement. If triangle ABC is congruent to DEF and DEF is congruent to JKL, then ABC is congruent to JKL. You get to take out the part that repeats here. All right, example 1. Complete with always, sometimes, or never. An acute triangle is blank congruent to an obtuse triangle. The rule on an acute triangle is they all have to be less than 90, and the rule on an obtuse triangle is one has to be bigger than 90, which means that this can never happen. 2, a polygon is blank congruent to itself. Well, any polygon is going to have all the same lengths of sides as itself and all the same sides as itself, which means this is always. 3, a right triangle is blank congruent to another right triangle. So it's possible for them to be the same, but they don't all have to be, which means this is a sometimes. 4, if triangle ABC is congruent to XYZ, then angle A is blank congruent to angle Y. A is not in the same spot as Y, so it doesn't have to be congruent. But you can have 2 triangles that have, or 2 triangles that have 2 angles congruent, which means this is sometimes. Now, if ABC is congruent to XYZ, then A is blank congruent to X. A and X are in the same spot in that name, which means that these always have to be congruent. All right, example 2 says in the diagram, polygon ABCD is congruent to FGHK. Find the value of X. So X is on the side length, that's GF. GF matches AB, which is over here. So 3X minus 6 equals 9. I also have an X in this statement, so I could use that and say that 4X plus 2Y equals an angle K would equal angle D, 44. The problem is there are 2 unknowns in that statement. So I'm going to first solve the first one by adding 6, dividing by 3, and I get X is 5. And now I can use that in this second one to find Y. 4 times 5 plus 2Y equals 44. So I substituted it in, subtract the 20, divide by 2. Example 3 says Maggie took the piece of fabric STUV shown in the diagram and cut it on the diagonal to make a scarf for her and her friend. Are the two pieces the same size and shape? Explain. So we know that this side matches this side. We know that this side matches this side. And the third sides would also match because they are shared by both. And we know this is a right angle. And we know this is a right angle. So that matches. Now, in order to prove that the other angles are congruent to each other, we have to go back to last chapter in which we said, because these are both perpendicular to the same transversal, these lines are parallel, and here's a transversal, which means angle 1 is going to be congruent to angle 4, alternate interior angles theorem, and angle 3 is going to be congruent to angle 2, same reason. So now I've got all 3 pairs of sides and all 3 pairs of angles. So the answer here is yes. If you went through the process, you'd have to acknowledge the congruent mark to the beginning, which is given. You'd have to add the reflexive side. You'd have to talk about the right angles, and then you'd have to do the alternate interior. But by explain, it really just means that all 3 pairs of sides and angles are congruent. If this was in a proof, obviously you might have to go a little bit further in detail. All right, speaking of, it says given SV is congruent to RV, so it's not marked, I'm going to mark it on here. SV is congruent to RV. TV is congruent to VW. And ST is congruent to RW. And angle T is congruent to angle W. Prove triangle STV is congruent to triangle RVW. Well, first of all, there's a lot of given. So let's SVRV, TV, WV, ST, RW, angle T, angle W. So from here, we have all 3 pairs of sides. And we have 1 pair of congruent angles. So we have to find a way to prove the other 2 angles are congruent. Hopefully you're seeing the vertical angles here. So I have to use 2 letters because, or 3 letters, sorry, because they're shared. But SVT is congruent to angle RVW. Or WVR, it doesn't matter the order there. And that's your vertical angle theorem. Now, in this section, we talked about the third angles theorem, which said if 2 angles of a triangle are congruent to 2 angles of another triangle, the third angles are congruent as well. So now I can say angle S is congruent to angle R, and that's third angles theorem. So now I can say triangle STV is congruent to triangle RWV. Definition of congruent triangles. Okay, that's the end of section 2. So into section 3, proving triangles congruent by side angle side. So we just left off saying that we had to prove that every pair of sides and angles are congruent in a polygon, even in a triangle, in order to prove that they are congruent. But now we're going to learn about shortcuts to proving triangles are congruent. By the end, we're going to actually know 5. But for this section, we're just talking about the first one, which is side angle side. So the definitions of included sides and angles are important to get into these shortcuts. And the first is the included side. The included side is the side between the given angles. So if I ask what side is included between angle A and B, A is here and B is here, it's the side that connects them, which would be side AB. If I wanted to know what was the included side between B and C, it's the side that connects those, so it's CB or BC. And lastly, if I want to know the included side of A and C, it's AC, because that's the segment that connects those. The included angle is the angle where the given side meet. So if I ask for which angle is included in AC and CB, AC and CB meet at angle C. So angle C is the included angle. If I said the same for where does AB meet AC, it's angle A. And where does AB meet BC, it's angle B. Again, where the sides meet. So this theorem, which is called side angle side congruence theorem, will be shortened with the acronym SAS. And it says if two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then the triangles are congruent. So we need two sides and the included angle in each. So if this angle side is congruent to that side and this side is congruent to that side, then I need the angle where they meet to be also marked as congruent. Then I can say these two triangles are congruent. All right. So example 1 says state which congruence methods can be used to prove the triangles are congruent, and if none, state NC. So right now we either have to have all the sides and angles marked as congruent, or we can use side angle side. That's the only one we know so far. So if I look at A, I've got one side here, that's one pair of sides. I've got this angle here, and I've got this second pair of sides because that's the reflexive side. But that is not the angle where these two sides meet. So this is not congruent. It would have to be here that we would know would be congruent. If you look at B, these two outer sides, the angle here and this side here, I also have the right angle, but I don't even need it because already I have side angle side. C, this time you've got the one pair of sides out here, one angle that doesn't even have the same tick mark as this one, which means they're not congruent. These would be congruent. I guess I'll use 3 since the other 2 are taken because they're vertical angles. But as it lies, you only have one pair of sides and one pair of angles, which is not enough information, so it's not congruent. D, you've got the outer two sides, the angle at the top, and the reflexive side. This is side angle side. And E, you've got two pairs of angles. And the third that are right angles, which means I have all 3 angles, but I know nothing about their sides, which means it's not congruent. Example 2, is there enough information given information to prove that the triangles are congruent? If there is, state the postulate or theorem. So we want to prove that ABE is congruent to CBD. Now, when they're overlapping like this, it's actually probably easier to draw them out separately and mark them with what you have. So this is here, this is here, and you have only this part here. And then the other one, B, D, C, this part is here, this part is here. Now the other difference is that here in the middle, the one that overlaps into both triangle is the same angle. So if I took this sliver A, B, D, and I added D, B, E to it, I'd get this whole angle, which is this whole angle. And if I do the same on this side, and I did D, B, E plus E, B, C, I'd get this whole angle, which would be here. So because you're adding the same angle to both sides of that, you also have that angle at the top. And this is yes, and it's side angle side. So we also added in a reflexive angle. We added in D, B, E to both. But because it was equal to itself, you could do that. Okay, example 3 says state a third congruence you would need to prove the triangles are congruent by side angle side. So far it's giving you ST is congruent to YZ and RS is congruent to XY. That's 2 pairs of sides. I need the angle, and I need it to be the included angle, which is where these meet. So I need angle S to be congruent to angle Y. All right, last up, and I know no one enjoys proofs, but the triangle proofs are hopefully a little bit easier. This is to prove the triangles are congruent. So we know right now we really just need to find side angle side, because we're not going to find all this information, but that's a shortcut we could use. So this one says, given BC is congruent to DA and BC is parallel to AD. So I've got my one pair of congruent sides, and they're also parallel. I need another pair of sides, and I have it already because this side is reflexive. So I can say AC equals AC, and it's reflexive. Now I have two pairs of sides. All I need is the angle where those sides meet. So here, this would be congruent. So the angle where they meet is here and here. How can I prove those angles are congruent? That's where the parallel lines come into play. If these two are parallel and this is my transversal, then those are alternate interior angles. And if the lines are parallel, alternate interior angles are congruent. Angle BCA would be congruent to angle CAD. And the reason is alternate interior angles theorem. And now I've got both pairs of sides and the included angle, which means triangle ABC is congruent to triangle CDA. And my reason, side angle side. All right, that wraps up the 5-1 to 5-3 video. Have a great day.